On February 28, 2026, the United States and Israel began a bombing campaign against Iran. In addition to the loss of human lives, an unacceptable fact in the context of defending human rights and peacekeeping, there is a consequence that rarely makes the headlines. Every explosion, every building reduced to rubble, every fuel tank that ignites, releases carbon dioxide into the atmosphere. War has a climate cost, and that cost is measured in CO₂.
Well, 2024, which is the most recent year for which we have emissions data, the emissions profile of the U.S. military at 47 million metric tons that year was greater than many countries, about the same size as the emissions of countries like Portugal. But one of the reasons we don't know all of the military emissions of every country in the world is that the United States fought very hard at the Kyoto Protocol negotiations in 1998 to exclude mandatory reporting of military emissions. So we know that...
That is Professor Netta Crawford from the University of St. Andrews in Scotland, co-founder of the Costs of War project at Brown University, and author of The Pentagon, Climate Change and War. She spoke to Marketplace, the United States public radio program, about the climate cost of the war in Iran. Her research has documented what most governments prefer not to count: the carbon footprint of military operations. If you have been following this podcast series, you will have noticed that we keep coming back to the same place: CO₂ emissions and the ocean's carbon cycle. We repeat it because it matters. About a quarter of all the CO₂ produced by human activity, from our factories, our flights, and the wars worldwide, ends up in the ocean. The ocean absorbs it, quietly. But how, and for how long? To answer that, I went to talk to two scientists in Bremen, Germany.
My name is Matthias Zabel. My role here at MARUM is I'm the head of the group Sediment Geochemistry, and we are interested in different kinds of science, especially of element and carbon cycle in the ocean. Mm-hmm. So what happens with these elements, which are how they are, if they are buried for a long time, centuries or decades or millions of years at the end, what happens with the carbon in the ocean?
Yes, my name is Enno Schefuß, and I lead the research group Molecular Paleoclimatology at MARUM.
Dr. Matthias will help us understand the ocean as the largest carbon reservoir on Earth and how scientists read the archives buried beneath the seafloor. And Dr. Enno will take us inside his laboratory, where he tracks individual carbon molecules through the sediment, like a forensic detective following a single fingerprint. Together, they are trying to decipher the climate history buried in the ocean floor and understand how the ocean has absorbed CO₂ over hundreds of thousands of years. What they are finding suggests that the system we depend on may be more fragile than we think. I am Juan David Escorcia. I report on the environment, the climate emergency, and the ocean, uncovering what's changing beneath the surface and what it means for all of us. This science journalism project was developed as part of the Frontiers Fellowship, funded by the European Union.
Part 1. The Ocean, Earth's biggest CO₂ reservoir.
When we talk about climate change, we talk about the atmosphere, emissions, concentrations, parts per million. But the atmosphere is not where most of the carbon is.
The ocean, at first, the ocean is the biggest player in this role, because the ocean is the biggest reservoir of carbon on Earth. And carbon itself, of course, plays a major role in life at the end. Huh? So we all consist of, we are made out of carbon at the end, with some nutrients and others. It's a lot of water, of course, but carbon is the most essential element, I would say, for life on Earth.
The ocean stores between 44 and 50 times more carbon than the atmosphere. It absorbs it, stores it, releases it. It acts as a buffer between us and a much worse climate. But Dr. Matthias is careful about one thing.
Now we have an increase of the CO2 in the atmosphere, that we all know from the data. And this is so huge, so fast. And there is, from my perspective, as far as I know, not a comparable situation in the past what we have seen before. We have seen higher temperature on Earth, yes, okay. And we have higher CO2 concentrations on Earth, yes, also okay. But this dramatic and very fast increase, this is quite unique.
Higher temperatures have existed before. Higher CO2 has existed before, but not this fast. In 300,000 years of geological records, there is no precedent for the speed at which we are forcing this system. And that means you cannot look at the past and say, this is what will happen next. The past doesn't have this chapter. So the question is, how do scientists study a system that has never been in this situation before? To find out, they read the archive.
Part 2. The Archive of the Ocean Floor.
Beneath the ocean floor, material has been accumulating for millions of years. Particles carried by rivers, remains of organisms, dust blown from continents, settling, compressing, building a record. At MARUM, they have one of only 3 core repositories in the world. Hundreds of kilometers of sediment samples drilled from the ocean floor, as we listened in the first episode of this series of podcasts. Each core is a timeline. Go deeper, and you go further back. But reading them is not straightforward, because every signal carries a question.
Then we have an information on a specific point of the ocean, of the seafloor, because there the core was taken from, right? But when we look to this very single point, it's a site study at the end. Now we have to know, okay, these signals were preserved at this place because we have this now, but the question is where they come from, for example. Can they be transported during the atmosphere by wind? Are they transported by rivers? Are they produced just at this site? All these are questions where you combine the different things together.
A signal appears in the core, you can measure it, but you don't know where it came from. It could have been carried by wind from a distant continent, dragged by a river from the coast, or produced right there on the seafloor. Without knowing the origin, you cannot interpret the signal. And if you get it wrong, everything built on that interpretation falls apart. So scientists build hypotheses. They test them with models. And sometimes the models break.
Mostly these questions only come up when you have the first results. Then you ask, okay, I analyzed this specific component, potentially never seen before from anyone else. And I can reproduce this also with my fancy machine. It helps me not if I don't know where it comes from which organism, or from which mineral, or from which process it will be released.
But to find what is missing, you need to look closer, much closer, because a sediment sample contains carbon from many different sources. Algae, land plants, bacteria, geological material, all mixed together. And traditional methods can only tell you how much carbon is there in total, not where each piece came from, not how old it is, not what organism produced it. To read those details, you need a different kind of scientist.
Part 3. The Ocean Carbon Detective.
When police arrive at a crime scene, they can see that someone was there, but to know who, they need a fingerprint. That's the difference between what most scientists do with carbon in a sediment sample and what Dr. Enno does. Most measure how much carbon is there. He reads the fingerprint. But this was not always his method. Years ago, as a young geology student in the Netherlands, he attended a lecture on organic geochemistry, and something caught his attention.
Then I went as an Erasmus student. I went to Utrecht in the Netherlands, and there were some lectures by people who were teaching organic geochemistry, and they were telling the students what is inside the organic carbon, right? This fossils, molecular fossils, remains, and how you can get the information out of it. And I thought that, hey, this is cool. This is new. It is mainly from the oil, right? So it was traditionally from the oil fields, right? Oil characterization of oils and reservoirs and gas and so on. But it's not used in climate or carbon cycle research at that time, 30 years ago.
A tool designed for the oil industry. Nobody was using it to study climate or the carbon cycle. Dr. Enno saw what others had overlooked, and that instinct changed the direction of his career. Back in his laboratory at MARUM, Dr. Enno can take a piece of the ocean floor, collected from those sediment cores that Dr. Matthias described, and isolate a single molecule from it. From that one molecule, he can extract 3 pieces of information. The carbon atoms reveal which organism produced it. The hydrogen atoms show what the surrounding water was like when that organism lived. And the molecule's age reveals how long it has remained buried in the sediment. It is like arriving at a crime scene with every instrument ready to reconstruct the timeline of what happened. While other scientists could only confirm that someone had been there, Dr. Enno wanted the full story.
So what it means that we are using molecules as fossils, right? So you could have bones from a dinosaur, but you could also have, maybe from the dinosaur, but also from other organisms, you have specific molecules that are left over, that are preserved in the sediment or in the geological records. And these ones you can use as molecular fossils. And sometimes just their occurrence tells you about some climatic or environmental conditions. Because you say, oh, maybe this means that this specific algae has been grown in the ocean, or this bacteria has been growing there, and these are specific conditions. We can also look at the isotope composition of these compounds, and they tell us something about the carbon source. What kind of carbon has these bacteria been eating? So what is the carbon flow from where is the carbon coming from and where is it going to?
Where is the carbon coming from? Where is it going to? That's what a detective asks about a suspect. And that's what connects Dr. Enno's molecular work to Dr. Matthias' system-level view. One sees the whole crime scene, the other lifts the prints. And a few years ago, one of those fingerprints led to a case that changed the numbers.
Part 4. The Cold Case. Carbon buried in the soil.
A few years ago, one of those fingerprints led Dr. Enno to a cold case in the eastern Mediterranean. For thousands of years, the Nile River has been eroding soil from the African continent and carrying it to the sea. Soil particles, plant remains, organic molecules, all deposited and buried at the bottom of the Mediterranean. By studying that material in the ocean floor, Dr. Enno found a way to understand what was happening to the soil on land. And that gave him a new element in the puzzle, the relationship between soil and carbon.
I mean, there is this whole discipline of soil. So looking at the carbon recycling in soils on land. And people do experiments. How is the soil carbon affected by climate change, or maybe also by anthropogenic use, right? If you do agriculture, how does it mobilize the soil carbon? Does it CO2 come out, or does it stay more in the soil, right? Because the soil is an important reservoir.
Scientists had studied this with field experiments, warming a patch of soil for a year or two and measuring the response. But Dr. Enno had something those experiments didn't. He had the sediment cores at MARUM.
I mean, this is the big advantage here in the MARUM, because we have this big collection of sediment cores, and people are still going on ship cruises. And with the marine sediment cores, often we have, when we go in front of the big rivers or in front of the dust plumes, we have like an integrated signal from a large part of the continent, which is, for me, is good because it tells me about a big area. Not just a small lake.
A sediment core taken from the ocean in front of a major river doesn't just record what happened at that spot in the sea, it records what happened across the entire continent that river drains. Every leaf, every grain of soil, every molecule that the water carried, deposited, buried, preserved. A record of the land written in the language of the ocean. And it goes back further than anything on land can offer.
And so we said, okay, we have the option, because we have these sediment cores, and they go back very different climates than today. So we can look how the soil carbon changed, let's say from the glacial time when it was very cold, very dry, to the modern time. So a much longer experiment than what people do in the field today. And we looked at this from the Nile River, so we looked at the age of soil-derived carbon in different horizons, and we looked at how the ages change. So the way the Nile River is always putting part of this soil carbon into the Eastern Mediterranean, and we get like a record, and the ages tell us something about how fast or how long has the carbon been in the soil.
The best archives we have for understanding the land are under the sea, and that is exactly what gave Dr. Enno the evidence that field experiments could never provide. Now, scientists already had a prediction for what happens to soil carbon when the planet warms. Their model said, for every 1 degree of warming, soils release roughly twice as much carbon, a factor of 2. That was the number everyone was using. Dr. Enno tested that number against his cold case, and the evidence told a very different story.
In the models, people were using a number of 2, right? So if you increase the temperature by 1 degree, you have 2 times more overturning of the soil carbon. And our number that we got from this natural experiment from Ice Age to modern, we saw 10. So it's like 10 times higher turnover, right? So that means when the temperature gets higher, like global warming, the soils will become sources of CO2, much stronger than we think.
10, not 2, 5 times higher than what the models assumed, which means that as the planet warms, soils could be releasing far more CO2 than anyone predicted. One fingerprint, one cold case, and a discovery that only the ocean could reveal. The soil beneath our feet holds secrets about carbon that are essential to understanding how our planet responds to warming. Thanks to the sediment cores at MARUM, Dr. Enno has brought us closer to reading those secrets, and with them closer to improving the climate projections that the world depends on. The uncontrolled accumulation of CO₂ emissions has accelerated a system that was never designed to work at this speed. The ocean is responding silently, but that silence is increasingly being decoded by scientists like Dr. Matthias and Dr. Enno. They study the ocean, they build the projections we need to understand. And they do it by following clues that would be unimaginable to any of us, molecule by molecule, layer by layer, with the precision of the best investigators at a crime scene. And what is the crime? It becomes obvious when we look at a world trapped in wars and dependent on fossil fuels that release more CO2 every year. Dr. Matthias explains how reacts the system.
So we use the information from the past to understand the very complex system as it is, and to give conclusive forecasts of that what will happen if the changes goes in a specific direction, for example. If we emit more and more CO2 to the atmosphere, what will happen? How reacts the system at the end?
I am Juan David Escorcia. I report on the environment, the climate emergency, and the ocean, uncovering what's changing beneath the surface and what it means for all of us. This science journalism project was developed as part of the Frontiers Fellowship, funded by the European Union.